VQE is an algorithm that's designed to find the ground state energy of a molecule, a task that's considered to be a killer app for quantum computing. It can be thought of as a guess, check, repeat algorithm. First, we guess the ground state energy, or ground state, with an ansatz. Then we check the energy of that state, and then we repeat. The good news is that VQE does not require too many gates. The bad news is that it requires too many measurements, and that's our focus in this check stage, how to reduce the number of measurements required. This graph here depicts the number of possible measurements that we might need to make for a 2-qubit problem. There are 16 such poly terms, or poly strings, represented as vertices. Our key observation is that while traditional VQE would measure each of these terms separately, terms that are connected with an edge are terms that commute, and it turns out that those terms can be measured simultaneously. Let's try an example. Here are the 14 terms that need to be measured for VQE for the hydrogen molecule. Edges are shown between terms that commute, that is, can be measured simultaneously. You can forget about the color of the edges for now. They're discussed in the paper. Notice that this graph has a min-click cover of 2. That means that we can cover all 14 vertices using just 2 clicks. And clicks are important because the click can be measured simultaneously. So on the left, naively, we perform 14 measurements. On the right, we've reduced it to just 2 measurements. This is the crux of our work. This idea leads to dramatic reduction in the measurement cost of VQE. The blue bars represent the traditional way of running VQE. The green bars represent our simultaneous measurement approach. You can see that the reduction in measurement cost goes from 7x to as high as 12x, and even higher for larger molecules. In fact, it turns out to be an asymptotic gain. We validated our technique experimentally by running on the IBM Q20 Tokyo machine. We measured the ground state energy of deuteron, the nucleus of the hydrogen isotope, and we found 11% lower error using our simultaneous measurement technique than the naive traditional way of running VQE. Our Python notebooks document all of our work so that future experimenters can reproduce our results and extend them further. Another important aspect of our work is code in Qiskit for generating actual circuits for simultaneous measurement. This turns out to be non-trivial, but we figured out a way to do it using the stabilizer formalism. Our paper is already having a large impact, with over 13 citations just in the past few months when it was released. Thank you for your consideration.